We are moving on to Chapter 3, which is about global warming. In this chapter, we're going to talk about what global warming really is, what can be done about it, if there's really any cause for alarm, because it is still considered a theory, and how we can assess the information from the popular press. Our atmosphere contains several compounds that get trapped in that trap heat from the sun. So here's the sun, comes in, and it traps the heat inside the surface. If they did not do this, the average temperature would be 0 degrees Fahrenheit. Keep in mind that the freezing point of water is 32 degrees Fahrenheit. Without these gases, we would not be able to survive. The greenhouse gases provide an extremely important function. Let's take a look at this graphic. Out of all the energy that enters the Earth, 25% gets reflected right back to the atmosphere. Only 50% of the rays even hit the ground of the Earth. Greenhouse gases are defined as gases that are able to absorb and trap infrared radiation and then warm the atmosphere. These include water vapor, carbon dioxide, methane, nitrous oxide, ozone, and CFCs. The buildup of these gases are making it have so much more energy is trapped than it's supposed to. This then makes the Earth warmer than it used to be, hence the term global warming. One word you might hear come up several times is anthropogenic. Anthropogenic means human activities such as industry, transportation, mining, and agriculture. Believe it or not, global warming was actually predicted back in the late 1800s. This was the Industrial Revolution, and Arrhenius, a scientist, noticed all the pollution that was being created. He said that doubling the amount of carbon dioxide would increase the Earth's temperature by 5 to 6 degrees Celsius. So back in the 1800s, they already figured out that global warming was going to occur. Burning fossil fuels such as coal, oil, and gas increases the amount of carbon dioxide in the atmosphere. Carbon dioxide is the product of this reaction. In the graph here, you can see that it's been a steady incline for the last 50 years. We started taking measurements around only 50 years ago, so we don't have any records prior to this. In order to take measurements that are older, we must find areas that have been around for an extremely long time. Scientists have realized that carbon dioxide gets trapped in the ice. So you can see in this picture. So they drill into the ice and look at how the concentrations have changed over the years. So they look at the concentrations from one year to the next. In the picture on the left, you can see the ice cap in Peru. You notice these horizontal lines going through it. These mark changes in the ice as the snow piles up. So these mark different ages and different years. By examining ice drillings that we saw in the previous picture, or also called ice cores, scientists have learned that there has been a dramatic increase in carbon dioxide in the past 100 years. Once again, remember the Industrial Revolution was back in the late 1800s. The current concentration of atmospheric carbon dioxide is 100 parts per million. That means for every 1 million particles, 100 of them are carbon dioxide, higher than it was the last million years. The graph also indicates a relationship between high levels of carbon dioxide and the ice ages. Notice that every time the carbon dioxide went up, there was an ice age. If we take a closer look at this graph, it indicates a trend that the temperature on Earth is increasing. That's this blue line here. However, it does not seem to be steady of an increase as the scientists originally guessed. If you notice the red bars, so these here, these are the average of temperatures for a year. There's an increase and decrease from one year to the next, unlike carbon dioxide, which is a steady rise throughout the testing. There was no decrease. Therefore, it is concluded that there is more going on here than just carbon dioxide increasing. Keep in mind that the graph you saw was an average of the entire globe. This means that not every area on Earth is changing temperatures at the same rate. Some areas have gotten colder, which are marked by blue. Some areas have gotten warmer, which are marked by the dark red. If you take all the temperature changes and average them together, then this is how we get the average temperature changes increasing. This graph shows the information for the last 400,000 years. The red line indicates the average temperature, while the blue line indicates the concentration of carbon dioxide. So this is the temperature, and the blue is the carbon dioxide. You can see that the correlation between the carbon dioxide, the blue line, and the temperature, the red line. As the carbon dioxide increases, so does the temperature. Please realize that correlation does not mean causation, which means that just because it happens doesn't mean that that's the reason it's happening. Therefore, more research must be done to really see how these things are linked. If we know the shape and structure of the molecule, we are better able to understand how they react. We use Lewis dot structures to help us draw the molecules. We briefly discussed that electrons like to be paired up. This is like a continuation of that theory. We can determine the number of valence electrons or dots that each atom has by looking at the periodic table. Remember in the previous chapter we had, for instance, 7A meant that this row had 7 valence electrons. 3A meant that this row had 3 valence electrons. Once you determine the valence electrons, you can draw dots around the chemical structure to indicate the electrons and how they are paired up. Draw them in a box with single electrons and then double them up. Let's try water. So H2O. If we go back to this chart, hydrogen is here. It has 1 valence electron. That means we have hydrogen with 1 dot. But we have 2 of them, so I'm going to draw it twice. Then we also have oxygen. Oxygen is here. It's in the 6th row. It has 6 valence electrons. So oxygen, first we draw them single, 1, 2, 3, 4, and then we pair them up, 5, 6. So it has 6 dots total. Look for the atom that has the most unshared electrons. So oxygen has 2 unshared electrons while hydrogen has 1. So I'm going to put that one in the middle. So I'm rewriting it. Then I'm going to put the hydrogens where those single dots are. I'm going to pair up the single dots. And that is our structure of water. Notice that these lone pairs here, or the unpaired electrons, still take up room, even though they don't get connected to something. Here's another example of methane. If we look on the periodic table, we'll notice that carbon is right here. It's in the 4th row. So that means carbon gets 4 dots. Hydrogen, once again, is right here. It's in the 1st row, so hydrogen gets 1 dot. Because there's 4 unshared electrons here, and hydrogen only has 1, carbon gets put in the middle. There's 4 of hydrogen, so there's 4 of those. So there's 1, 2, 3, 4. And each of them gets their own single dot. Go back and we pair them up. This one doesn't have any unshared electrons. All the electrons are paired up. These are different ways in which methane can be depicted. The molecular formula on the top is very informative. It's important and easy to write, but it does not immediately help tell you what it looks like. It just tells you what's in it. The loose structures provide more information. Not only does it state the atoms, but also states the bonds. So here's the electrons that got paired up. Here's the bonds. The third version goes one step further to show you how it would look 3D. The wedge means it's coming out. The dash means it's going away. This is called the space filling. It's able to show you the space which the atoms actually take up and how it's more accurate. By knowing the 3D arrangement, we can better understand how energy is absorbed by the molecules, and we will discuss this in a minute. The 3D representation is a reflection of what is called the Vesper theory. Valence shell electron pair repulsion. It's pronounced Vesper. This theory states that since all electrons are negatively charged, they will try to get as far away or repel from each other as possible. Things that have the same charge typically repel, while opposite charges are attracted to one another. This is an excellent representation of the Vesper theory. Notice the tripod is as spread out as possible in all directions. This is a perfect depiction of the tetrahedral figure, which is what methane is, the molecule on the previous slide. Notice how the carbon is in the middle, carbon, carbon, while the 4 hydrogens are surrounding it in all different directions. Hydrogen, 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 hydrogen. Whereas hydrogen on the poles would be here, 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 and here. The atoms are as spread out as possible in all 3 dimensions. Even if there are 2 electrons there with no other atoms bonded to it, it still takes up space. So these unshared electrons still take up space. So if we took the tripod of the previous slide, so if we go back here and took this tripod and take away 2 of the hydrogens, these would still be here in this structure. They would just be filled in with dots instead. So these would be like bonds here, but they're filled in with dots instead. Water is an example of this. Oxygen has 6 valence electrons, which means it has 2 unpaired electrons and 2 paired electrons, which go to the bonds. The 2 that are paired push the hydrogen atoms down. You can see in this chart how the unpaired electrons relate to the shape of the molecule. For instance, carbon does not typically have any unshared electrons. In the first row, all the unpaired electrons are attracted to other atoms, giving 4 bonds per the central. This is why there's a 4 here, 3, and there's another one here, 2 and 2 for 4. That gives us tetrahedral. That's the one that we saw with the tripod. In the second row, nitrogen, it has 5 valence electrons. This gives an arrangement of 3 unpaired electrons in 1 paired set. The 1 paired set acts like having a tetrahedral arrangement, but taking away one of the legs. This makes it look like a pyramid, which is why it's called trigonal, or triangular, whichever you want to pronounce it, pyramid. Notice that there's 3 unshared electrons here. Nitrogen's in the 5th row. 1, 2, 3, 4. One of them is paired up. The other ones are single. Finally, in the last row, oxygen and sulfur is the central atom, and they have 6 valence electrons, which means that they have 6 dots around them, which means 2 of the legs from the tripod have been taken away, which means they are only bonded to 2 other things. That's giving what they call a bent structure. Notice that the angle decreases as the paired electrons, as the lone pairs increase. This is because the paired electrons take up more room than the bonds to the other atoms. Let's take a look at carbon dioxide now. The carbon originally has 4 single electrons. It's in the 4th row. Instead of bonding to 4 different things, it has 2 double bonds to oxygen atoms. So these 2 are going to go to the oxygen atom, and then there's another oxygen atom on this side. And these 2 go to here. That's where we get the double bonds from. Since there are no unpaired electrons left on carbon, there's nothing to push it down. So therefore it stays flat. Notice there's no lone pairs here. So it's linear. Now that we understand how the atoms are bonded together, we can discuss how they move around in space. Nothing ever stays completely still. The bonds will move as it absorbs energy. It can move in 4 different ways. Think of it as vibrating or holding a slinky and having 3 different people holding it and moving it around. A represents if 2 people were on the end and are pulling it in and out at the same rate, while the person in the middle stays still. B is if one person was pushing it while the other one was pulling it, and the middle one continues to hold still. C is if the person in the middle was pulling the slinky up while the people in the ends were pulling it down in opposite directions. And D is when the person in the middle pulling in one direction while the person in the ends were pulling in the other. These movements are detected through a technique called IR imaging, or infrared. Remember, infrared is another sun ray, or another energy, that's actually less energetic than the visible light. But the molecules can still absorb this energy. The compound is put into the machine that forces the molecules to absorb the radiation. Then the computer detects the bond's movements. This is a printout of an IR machine will provide. Notice the dips where the energy was absorbed. That's detecting the different energies and the different wavelengths that the molecule was absorbing. As IR radiation is absorbed, the amount of radiation that makes it through the sample is reduced. So the molecule is absorbing that energy. So as it's going through the machine, suddenly there's a big dip in energy where the IR radiation was still there because the molecule absorbed it. Now let's relate this movement to absorption of UV radiation. So microwaves are the longest wavelengths in this picture. All it's doing is spinning it. It's really not making the bonds do anything special. The infrared is making them move, whereas the ultraviolet would actually break the molecules' bonds. That is all we're going to discuss with this section. We're going to move on with the next section of how this relates to global warming.